So it has just hit 1:30 here in Germany. Welcome everybody to the closeout session for the Vector project. We've just spent the last couple of days working with one another. Many of us have been here in the room together in Germany, but of course a number of our project partners have been dialing in online, and we've been not only presenting some of the really exciting results to one another, but also reflecting on the project as a whole. And some of the really lovely reflections have been how much we've enjoyed working with one another, especially across different disciplines, and how much we've got out of learning from one another and getting to know one another as well, which has been really fantastic. So the next 90 minutes will be our closeout call. What we're going to do is going to invite each of the leaders from the different areas of research to give just a highlight of some of the work that their groups of researchers have been undertaking. And then we're going to open up for questions at the end of today's session as well, so we can really see if you have any ideas, questions, comments, thoughts that you would like to share with the Vector team as we go into the final wrap up for the project. So with regards to all of this, what we'd like to just focus in on now is I'm going to pass across to Chris, who has been one of our, very much leading on everything to do with communications and a lot of the impact side of Vector. And Chris is going to show us where you can find lots of this material on the website. So we, of course, do encourage you to listen to our fabulous researchers and leaders, but also if you'd like to go exploring some of the deliverables, some of the outputs on the website as well. This, of course, is going to exist very much after the end of the formal part of Project Vector at the moment. So Chris, over to yourself.
Brilliant. Thanks ever so much, Sarah. So hopefully everybody can currently see on the screen shared there the Vector website. You'll see on the home page there's a little bit of information about what we are as a project, what we've been doing over the last 3 years, and as well as that, there is a carousel of lots of the fantastic outputs of the research project being displayed and rotating through. Now, this is only a subsection of all of the fantastic results that have come out of the project. If you navigate through the website to the Vector portal and click that button up in the toolbar, you'll come to see the full range of results that have been produced throughout the project that we can share with you publicly. So in this, you'll have all of the deliverable reports that are open access to the public, the same as those on Cordis, and there'll be a whole bunch more of these added in July, through to peer-reviewed papers and publications, the documentary 100 Perceptions Raw Materials we produced as part of this project, Who Decides, interactive games, exploring stakeholder engagement, social science simulators, education resources, podcasts, videos, info packs, and other geotechnical toolboxes and resources as well. You can also find out more about the project through the Vector YouTube channel, where a whole host of our webinars and other video and media related content is stored. All of this will be updated over the next few years, so make sure to follow the LinkedIn account that we are posting in the chat over and over again to make sure you catch all of those updates. But that's where you can find all of our outputs. Thanks, Sarah. Back to you.
Brilliant. Thank you very much, Chris. So first, just to keep things rolling, I'm going to invite our leader of all things Vector to the stage. And I know that Chris will spotlight the fantastic Richard. So Richard is here with us in Germany at the moment. Richard, perhaps if we can pass over to yourself so that you can give us a bit of an overview as to what Vector is all about and what the original aims of Vector were. Richard, over to yourself.
Yeah, thank you, Sarah. So Vector is born from a paradox and a challenge. So what is this paradox? So we want to mitigate climate change. So for that, we need to change the way we get our energy. We need to transition to a green energy. And by doing so, it means that we require a lot more of critical raw materials like lithium, cobalt, copper, and so on. Some of these elements were not mined in the past. So it means that we have to find new ways to acquire these minerals. So that's the first paradox. By transitioning to the green energy, we need more of these critical materials. So the question is how we can do that. So there are many ways to do it. We can recycle, we can reuse, but that will not help in the short term. So we know that in the next couple of decades, we will have to rely on new extraction of these critical materials. So that is a challenge. The problem is, what we found out is that finding these new raw materials faces one barrier. In the past, to find raw materials was mostly a technical challenge. Now what we found out is that it is mostly a social science. And it means that we have to include all stakeholders in order to be able to create new mining projects. So Vector is about that. How can we find ways to make mining more acceptable and to put mining in a sustainable society? So we know that mining itself is not sustainable. Yeah, so that we know for sure. But what we can find out is, can we put mining in a sustainable society? Do we want that? So for that, we need two things, or at least two things. One, we need the new technologies that will allow to mitigate the impact of mining on the environment. And the other aspect we need to research on is, how can we together find a way to make mining project acceptable for all. So not only for shareholders, but for the local communities and all the stakeholders that are involved in a mine. And Vector was built on that. So it means that we have one work package dedicated to develop new technologies to find these raw materials, one work package dedicated to address the social aspect of mining, and the third one was to integrate this information and make sure that using new technologies, we can integrate and add value to this data, mostly using machine learning. And we had another work package which is very, very important, combine that and making sure that we can disseminate and exploit these results. So that's the only thing I wanted to say from my side. We will have now a series of highlights from the different work packages, and I'll hand over to you, Sarah.
Excellent. Thank you very, very much for that, Richard. So exactly as Richard has said, Vector is composed of a number of different work packages. And for the last time, I'm going to do this piece of choreography. So Geertje, you're going to be very glad with regards to this. So Vector is composed of geoscience, of social science, and of data science, bringing it all together to enable us to understand where might we be able to go, or what kind of aspects do we need to understand to find those materials that we may need to extract for the energy transition. And exactly as Richard said, this is part of a much broader materials challenge. Ideally, of course, we make use of all those materials that are in circulation. Ideally, we reduce the amount of stuff that we need, but where we do perhaps need to be aware of what is in the ground, where do we need to go? What are those different aspects that we need to be considering with regards to that? So to welcome to the stage the first aspect of that piece of choreography is Professor Sarah Gleeson, who led on the geoscience component part of Vector. Now, we had a wide range of different researchers who came together for this, and Sarah will be sharing with us, I know the slide is just being shared with us just now, will be sharing with us some highlights of the amazing world of things like geophysics, etc., which were used to enable us to better understand where might we be able to use geoscience to better understand that world of exploration. So with that, I'm going to hand over to the lovely Sarah Gleeson.
Hi, good afternoon, everybody. Yes, I'm going to attempt to show you some of the highlights that we produced in work package 2. And just, yes. Great. So sedimentary basins in Europe host a large proportion of European metal deposits, but a lot of those deposits are not exposed at the surface anymore, so they're buried in the subsurface. And so we need new approaches to explore and find ore in the subsurface. And the techniques that we want to try and develop need to have as low an environmental impact as possible. So in Vector, we identified 3 areas to do further study. So one was in the Midlands in Ireland, where there are a series of zinc and lead deposits. The Kupferschiefer in Germany, in Spremberg, is where we see copper deposits. And then we worked on some historical samples that we had in an archive from Jadar, which is a lithium system in Serbia. Ooh, next slide, please. No. Okay, so what we actually wanted to do in our 3-year project was to test some new geophysical techniques with potentially lower environmental impacts, and I'll explain a little bit about those in a moment. But we also wanted to collect samples and have geological information, geochemical information, geophysical information from the same samples, and basically then give those data to our colleagues in work package 4 for deep learning techniques. And then we wanted to see if we could identify some chemical vectors or some mineralogical vectors that allow us to find mineralization in the subsurface. So our work package was divided into 4 sections. And the first section was really collecting, bringing data together that had been previously collected and building 3D models of the geology. And so this involved re-logging a whole bunch of drill cores that have been collected, looking at hand samples, and then trying to collect or put all this information into softwares to look at it, look at the subsurface in 3 dimensions. And I'm just going to give you an example of one of the places that we studied, and that's Stone Park in Ireland. So on the right here, there's a geological map. So all these different colors are different kinds of rocks. And all the little black holes are drill holes that have been drilled through this sequence. And you put all this information into the 3D model, and this is a slice going into the earth here on this cross section. And you get here, you can see it's more or less a layer cake stratigraphy. The different colors are different rock types. The drill holes can be put onto these models as well. And the mineralization are these red areas here in the subsurface. Now, one of the things we wanted to do was to see if we could improve these models by getting some more information. And one of the techniques we wanted to test was passive seismic imaging. And this is a technique that uses what's known as ambient noise to image the subsurface. So you're basically putting sound waves into the earth, and those waves are just coming from the local environment. So it can be coming from the oceans, it can be coming from wind, or in fact, it could be coming from big trucks traveling on roads. And whether we can measure those waves and then use them to say something about the structure or the type of geology in the subsurface. And these passive seismic surveys just use these very small geophones and a battery, and you can place them along roads and collect data in a time series over maybe 6 weeks or even shorter times. And we showed that this type of technique does work well in Ireland. There are other techniques for getting seismic images of the subsurface that are much more expensive, involving using seismic trucks to basically hit the earth to send out those sine waves. And what we showed is that using this other more environmentally friendly technique, you can basically resolve some of the structures in the subsurface to about 1.6 kilometers, which is quite a good depth. And that the results from our survey do basically match some of the results from these more expensive surveys that were carried out previously by the companies. So we're shown that this low-cost passive seismic tomography can image the subsurface, at least in Ireland, in an efficient way compared to expensive active reflection seismics. Now, it wasn't all good news, because we also had a field site in Germany, which was next to a town with an open pit coal mine, and it didn't work in Germany. And our scientists are working on why that is the case, but probably some of the underlying assumptions that have to be met for passive seismic to work were not met in Germany. And so this is sort of an interesting result. It's a null result. And one of the thinkings why this may be is that the ocean around Ireland is a constant noise source that's stationary and isotropic and actually helps us see through the earth. even though our field site was 70 kilometers away from the coast. The other possibility is that this open pit in Spremberg might have also affected the results. Now, in the second part of this work package, we also looked at petrophysics. So this is when you measure the physical parameters of the rock. So for example, how a rock conducts electricity, whether they're magnetic or not, or how these seismic waves pass through them. And then you can use those data to basically better constrain your magnetic, your seismic, your gravity models of the study area. So here we are again in Stone Park, and this is a slice here through Stone Park following this seismic line here. And these are the green holes now, or the drill holes. And this is basically a map of the different physical properties of the rocks that we see at Stone Park. And you can then take these physical properties and look at some old seismic surveys and help you to make better interpretations of them. So now this is a slice basically along that line. These are the sound waves, the seismic waves passing through the Earth down to a couple of kilometers here. And now you can start to pick out, these are different geological units in the subsurface. And you start to see faults basically here that we hadn't seen originally in our initial model. On top of that, you can look at something called magnetotellurics, and this is using the Earth's natural electrical field when it goes into the Earth, and look at the different ways that rocks are resistive or conductive. So we did a survey here in MT, and this is sort of the pattern that you get here. And when you put it with the seismic survey, you can see areas where you get highly resistive rocks, and this is correlating with the volcanic intrusion that they have in Stone Park, and also low resistivities, which again suggests there were fluids maybe coming up these faults. So just to sort of pull this all together, this is where we started off. This was our 3D model of Stone Park. It was quite simple, and now we're seeing this complexity, which will really help the company figure out what they want to do next and where to drill their next holes. This third part of this work package was to actually look at the chemistry of the rocks instead of the physics of the rocks, and the mineralogy, the minerals that form the rock. And so there were two techniques used here. One is hyperspectral imaging to make maps of minerals in the core. And the other one was a series of techniques called quantitative mineralogy. And they allow you to basically figure out the percentage of different minerals that you have in your rocks. So the hyperspectral work was a sort of very exciting part of the study. This is a system whereby you can feed in your core tray and you basically scan your core. You've got 3 cameras and they record spectral information in every pixel. So you're just taking a bunch of information from the core. And you're measuring how light is absorbed or reflected in different minerals. And they have these characteristic patterns. So these are all different minerals with different patterns. And you collect a huge amount of data. But then, unfortunately, the hard work starts because you've got to turn these squiggles, the signals, into actual percentages of minerals and maps of minerals. So we did a lot of work on this. Sam Thiele did a huge amount of work with Yongwei Kim, trying to figure out how to quantify this, using all kinds of statistics and producing workflows that you can feed the data in, and to end up with something that looks like this, which is actually a map of the distribution of different kinds of elements. It's color-coded so that it's easy, for example, for the end user, like a geologist, to read. And you find basically that you can make these maps of different families of minerals. So for example, this is the Kupferschiefer in Germany. So here is the area where the copper is. These are the rocks underneath the copper. This is the rocks above the copper. And you can see underneath the copper, you get minerals that are very typical of sandstones, for example. On top, you get minerals that are very typical of limestones. And here, you get minerals that are changing in abundance as you get closer to the copper mineralization. So these are the minerals we're really interested in to be vectors for mineralization. We would like to see, if you drilled a hole somewhere, if you see these minerals, does that tell you that there might be copper sulfides somewhere close by? And one of these minerals is illite. And I just wanted to show you an actual rock picture. This is a slice of rock. This is 10 microns. This is a copper sulfide mineral here, filling in a sandstone. And if you take a slice through this rock and you use a really, really high-powered microscope, this is transmission electron microscope, you basically find this mineral illite. And we were quite surprised that in between the sheets of this mineral illite, there are copper chloride phases. So this tells us that this mineral illite definitely formed at the same time as the copper mineralization. So the last thing that we did was actually looking at the elemental composition of the rocks. So companies routinely analyze their rock samples for actually most of the elements in the periodic table nowadays. Sometimes there are challenges when you're dealing with older surveys, because sometimes they didn't measure all the elements, or they were using different labs with different techniques. And so one of the things we wanted to do was collect all that legacy data, level it, do sort of quality assurance and quality control on it, and then collect some new data and see if we could identify any vectors using that approach. And I'm just going to give you one example. And this is, again, back to the Irish ore field. And here there's about 6,000 samples were looked at. And looking at the statistical distribution of the elements, what you find in the rocks is you tend to get elements that are associated together. So for example, if you have a carbonate rock, it's not too surprising, you get calcium, magnesium, and strontium come together. If you have a rock like a sandstone or a siltstone, you get these elements up here. But the purple elements here are the elements that occur together in mineralization. So you get arsenic, zinc, cadmium, for example, thallium. These elements occur together. So if you find those in your spreadsheet, it gives you an indication that there's some mineralization in the rock. And one of the things that was done with this by Joe Magnol was that he identified that pre-ore pyrite, so the pyrite that's in the rock naturally in the background, and pyrite that's associated with sphalerite have different compositions. And the biggest difference in the composition is in terms of arsenic and also in terms of cadmium. So you can tell the difference between this background pyrite and the pyrite associated with the hydrothermal system. And so he basically suggested that if you plot up your data and plot arsenic and cadmium together against rubidium, that this will give you an indication that you've got more hydrothermal pyrite in your sample, and therefore you might be nearer to the ore system. So that's just an example of some of the things that we did in Vector. What have we done all together? We relogged about 15 kilometers of drill cores, and we put them in 3D models in the 3 study sites. We produced new geophysical data and petrophysical data sets in Ireland and in Germany. There was a lot of drill cores scanned by hyperspectral imaging, and quantitative mineralogy was carried out in a subset of samples. And as I mentioned, there were some really big lithogeochemical data sets were leveled and interrogated and interpreted. So overall, what we've done is we've shown that these passive seismic techniques have some use in terms of exploration, lower cost, maybe a first step in exploration in some place like Ireland. We've also shown, we developed a separate way of measuring these electrical signals, which is also involves less equipment and energy consumption. We've produced a lot of workflows about how to deal with these large data sets and how to then visualize the data, which is just more practical for the end user. And we have identified some chemical and mineralogical vectors. So I showed you how arsenic can be used basically in Ireland as a vector towards ore. And these are some of the people involved in the project. And that's it, Sarah. I'm handing back to you.
Fantastic. Thank you so much, Sarah. That's absolutely amazing. And I think it cannot be understated how exciting some of these results are. This particular group of researchers have not only proven that you can use passive seismic in ways that have never before been tested. I think it's amazing that we can use that natural power of the waves to understand so much more about the rocks beneath our feet in Ireland, all the way through into saying, well, hang on, if I go and do some chemical analysis of some rock samples, what does that then tell me about where I could go and look for perhaps some of those critical materials that we need for the energy transition? So I think perhaps Sarah was being fairly modest with some of those conclusions there. There's some really exciting breakthrough science that's been coming through within Work Package 2, which of course was the geoscience focused work package. But to be honest, there's no point in doing that, and I say that knowing that Sarah Gleeson is just over here to my right, but there's no point in understanding what might be in the earth beneath our feet if we don't actually also try and understand what's going on with regards to people and society, and what are the different perceptions and feelings and understandings with regards to those raw materials that we either need within a society, or how do we source them? Where should these materials come from? And so this is where the social science part of Vector comes in. And sorry, I should be doing the actions, shouldn't I, Fetchy? So this is a case here where we've now got the data science, and we've got some really exciting breakthrough science going on there. But then we also need the social science. So what's going on with regards to that? Because it's only when we actually get the understanding of both of those two worlds, can we begin to say where might be a good place to understand where to get these materials either from, or at least understand the discussions that need to be begun to be had. So once we start sharing the slides, I will then shut up and pass over to my favourite environmental psychologist. I will pass over to Fetchy. Over to you.
Thank you so much, Sarah. So yes, just to reiterate what already was mentioned by Richard and Sarah, could you click on that so that this works? The motivation behind Vector is to think about the supply of Europe's and the UK's Green Deal, like decarbonisation targets, and there's lots of technical, economic, environmental and social challenges with that. Now, Work Package 3 is mainly focusing on these social challenges, because you can work out where on the geology, where are the minerals in the ground. You can work on the technology to get it out of the ground. You can think about the economics of making that work. But if at the end of the day, the end result doesn't benefit society, this is why we do it, then you have social challenges to deal with. So Work Package 3 is mainly looking at these social challenges from the perspective that could we think about human-centered solutions to these very complex challenges, meaning that how does it ultimately benefit all of us and society, and not just be technically or environmentally optimal. So unlike the geological world, I am going to assume that that hasn't changed much over the last 3 years. Now, I know there's changes over time, but it won't be that quick. Social sciences and the social challenges change continuously. So what you probably have seen in the news is all sorts of changes where minerals, Green Deals, and, for example, Donald Trump interested in buying Greenland, or think about a minerals deal with the Ukraine, is changing the political landscape, is changing the way we think about the supply of decarbonisation targets. We also have the beginning of the project, the European Green Deal. The UK and most other member states also have the equivalent of decarbonisation objectives. That was there from the beginning of the project. Halfway the project, the European Union released the Critical Raw Materials Act, specifying in way more detail how the EU intends to supply their Green Deal targets. But then very recently, the ESG requirements for industry, so how should they ensure there is environmental, social and governance security, has been discussed by leaders in the EU. I'm saying all of this to indicate that the social reality of the challenges that Work Package 3 is working in is constantly changing. And therefore, we constantly have to adjust our research to the reality of the time. Now, to some disappointment of some partners potentially in the project or people out there watching this, some things haven't changed. I'm just showing you some data of 2020, where you can see that the mining sector scores rather low in terms of how socially responsible they are perceived by the general public. And I'll come back to that feature, so hold that thought. This is the team working on all these social challenges, so presenting lots of work done by people on this sheet. And the first part of the work was actually looking at that trust element, because what we assumed is that if trust is low, then maybe the reason could be is because there's ethical implications. So some of the pilot work we did was actually highlighting that indeed over time as well, the mining sector doesn't score so well if you compare them to different stakeholders that work on the decarbonization targets. Now, for example, it's quite interesting because if you look at the renewable energy sector, which highly relies on the supply of raw materials, they score way higher. So if you think about ethics and you think about trust, we're actually interested to think in a little bit more detail. Why might that be? And if you think about trust, you can trust organizations for different reasons. You can trust an organization because they're competent, they know their work, they can deliver what they promise to do. They're competent in what they're doing, and therefore you might trust an organization. You can trust an organization for its integrity. So how honest are they? How transparent are they? How much do they actually comply with their commitments? And then you might trust an organization because of their benevolence. To what extent do they benefit society? To what extent is there are they acting in the interest of the social world around them? Now, we did a comparative study in 4 countries where we see consistently trust in competence is relatively high. Most people think that the mining sector can deliver their job well enough. Where we see trust is way lower in benevolence. So these are areas where the mining sector can work on. And that feeds into the second part, tasks, that was delivered by this work package. So in this part, we were looking at that concept of benevolence. And benevolence from the perspective of an organization is often referred to as something called shared value. And shared value is defined as a business practice or policy that both generates a competitive advantage for organizations while simultaneously also benefiting society. So the idea behind shared value is that an organization finds an element in their local social environment that they can address, which will actually add value and benefit the organization or the company as well. Now, in this work package, this concept has been discussed heavily. It was defined and conceptualized. And the next step was to empirically test whether we can actually find data that matches that idea. So how can we identify shared value in regions? and how can we create opportunities for this shared value to be brought to the foreground. And that all led to the creation of something called the Shared Value Index. And that index has recently been released online. You can see a screenshot on the slide here with a link where you can have a look at it. And effectively, what it indicates is how can organizations find and share that shared value in specific locations. So what should they consider? The third task in this work package was this is still part of the second task, of course, is to think about those human-centered solutions. So taking that perspective of shared value, recommendations were given to business models. How can mining sectors improve their business models to create that shared value? But the same applies to policy and policy frameworks. How can they be improved to better have that human-centered approach at the core of these frameworks? How can we make sure that society and societal benefits are part of them? And so there's a whole list of deliverables available after the project on the website, and reports and papers written that specify these details. Now we're thinking about mining sector, land users, geologists, then very often there's lots of focus on technical aspects, and they're of course really important. But those who also go out and go into fields and have to communicate with local farmers and landowners and communities will actually need some training in how to deal with these social elements. And to that end, partners in Cezanne Associates and SIK have put together a game. It's called Who Decides? And this is part of the professional modules to educate land users and geologists in what social communication challenges may they meet when they go out into the field. And it presents all sorts of challenges in stakeholder communication, in resource limitations, in dealing with local communities or landowners. And it's a very interactive game that, again, you can find on the Vector website. As part of all the communication tools that we have developed in this work package, the Vector Simulator is another communication tool that can be used by different stakeholders. It can be used by industry, it can be used by policymakers, or it can be used by educators who are trying to explain the link between the need for raw materials if you want to meet targets of the Green Deal. So the Vector Simulator is trying to explain and highlight the consequences of choices that people make. Again, that is also available on the website. Now, the third task that Work Package 3 was dealing with is not just taking the perspective of industry and practitioners, but also look into how can we communicate to the lay public about the need for raw materials to meet decarbonization goals. And to that end, we looked both at formal and informal educational settings. As for informal educational settings, work that was done in UCD is looking at how can we engage the general public who visits festivals, different events into these conversations. And to kickstart those conversations, UCD has created this Green Deal kit, public communication, public engagement toolkit. Now, the Green Deals exist of a starter activity that helps people to engage in these conversations. And it's really a shopping activity where people get different minerals and they can use them to buy enough materials to build certain technologies. Now, as a spin-off of that basic idea, currently a digital game is under development, nearly finished, so keep an eye out on the website to see that. And on the basis of that idea, the Green Deal's mineral game was developed together with Work Package 5 to be part of the documentary that Chris and Sarah mentioned earlier. Now, that tool doesn't just go into informal educational settings, but also into more formal ways of helping teachers, helping educators to bring to the foreground and part of the science discussions that are ongoing in educational settings. How can we make sure that children, that teachers understand this part of the dilemma? And to that, and the partners in UCD, Cezanne have set up different communities of practice with educators, with researchers, with scientists, to discuss the educational curricula, to think about how can we make teachers aware of certain dilemmas as part of making creating a decarbonization targets and meeting climate change challenges. So to achieve that, we have two different outcomes here. One is a really interesting network of all these teachers and scientists as a part of a Next Act website, but also an educational pathway which highlights the role of education to make sustainable teaching more to the foreground and guide educators in how they can build this into their curricula. Now, I think something interesting that came out of this work package is that lots of the different tools that we created are now being discussed as can we make them part of that formal educational setting to, at the end of the day, create this education for sustainable development and global citizen goal that the EU has set. So finally, the whole setup, as Sarah explained, is that data from geoscientists and social scientists together are used by Work Package 4. I'm making the movement. Are used by Work Package 4 to together integrate this data into an interactive platform. And I'm sure that Richard will talk about it later on. So we handed over data to Work Package 4, who then created this interactive tool. But in Work Package 3, we then set up a user evaluation experiment where we're testing out how users, how stakeholders, how potential target groups would interact and make use of that particular platform. And we feed that information back to Work Package 4 to improve this tool. So just to round up and hand over to Sarah, as I started with, the purpose of Work Package 3 is to think about human-centered solutions to current supply issues. And so if you look at certain outcomes, and I could have put more, except for it didn't physically quite fit on this slide, we built lots of interfaces, and I put the interface developed by Work Package 4 on this slide as well, to think about what can we create as a consortium together to generate those human-centered solutions to these supply issues. And with that, I'll hand back to Sarah.
Thank you very, very much, Hershey. Fantastic. So what we've seen there, of course, is this amazing world of listening to and interacting with people, because people are just as important as the rocks, and I say that as a geoscientist myself. Something from a very personal perspective within Vector has been very much around, well, how do we create that environment, that ecosystem that really welcomes the bringing together of lots of those different disciplines. Because it's only by bringing together those disciplines that we stand even a smidgen of a chance of being able to address this materials challenge that we're surrounded by at the moment. So the next person that we're going to welcome to the stage is, of course, the person who binds all of this together, or the work package that binds all of this together. Now, whilst, of course, data isn't the only thing that we've managed to get out of Vector to date, of course, all of these amazing relationships and ability to work together. But work package 4 is where we really do bring together these data sets and we say, okay, so what? What does this actually tell us? So with that, I'm going to hand over to Richard. Thank you very much.
Yeah, thank you, Sarah, for the link. So yeah, work package 4 was there to integrate data and try to find out if we can add value to this already amazing data. So I think Sarah Gleason and Hertje convince you that already at this stage they had substantial results. What we try to do is using machine learning techniques to try to push these limits a little bit. So this consortium was built on the collaboration with industry, and here we were very lucky to have two startups, Terraigma and Terranta, who were responsible to develop some of these tools. So I wanted to start with AI because we know it is a little bit of a difficult topic. And I wanted to remind you that AI is the engineering of machines that mimic cognitive function. It's not what we are doing at all. We are not trying to do that, and we are not trying to use personal data to infer information that would be used against individuals. We are not doing that at all. What we are doing is a bit of data science, so the use of different mathematical technique to make inferences. And we use patterns and objects from images on video, so it's called computer vision. And we use these techniques to do machine learning and deep learning, so to infer patterns in data that can be very, very complex. So Vector is here. We are very, very far away from what could be AI. There is a definition from the EU, it's called an AI system. So we are using components that could be used for AI, but we are not using artificial intelligence, and especially not to infer results that could be used on an individual level. So the first aspect that we were looking at is, can we integrate all this information coming from work package 3? So you heard from Sarah Gleason that we have geophysical data, geochemical data, geological data, and we need to merge. And for that, we are piggy riding on an open source software that has been developed for a couple of years already. But here, what we were doing is adding some new open source functionalities in order to improve the processing of this information. So you see that what we want to have is what we call a digital twin of the Earth. So before we even start drilling or having access to the site, we want to have as many information as possible. So for that, we use geophysical data, we use surface data, we use existing legacy data that could be borehole, but could be something else. We mix that together and we get a comprehensive geopolitical model. So it is very powerful. We try to make it as easy to use as possible. It has advanced features, and hopefully in the future it will be more user-friendly. It's an open source software, so it means that we don't have the capacity to maintain very, very fancy user interfaces, but at least we are able to use that for geological modeling. So it looks like that. So what we get is a 3D model, and you can interact with the model quite easily. So what kind of data can we put in these models, and how we can use that? So Sarah Gleason told you that what we have are, let's say, petrological, chemical data, and we had also the hyperspectral data. And the idea here is to combine this information. So if you remember the scale of this geochemical data, it's on a tiny little piece of rock. and it's very costly to make that at a very large scale. And on the other hand, we have hyperspectral data, and that we can acquire over a very, very large amount of cores. And what we want to do is combine them. And we get the best of the two worlds. We get the accuracy of the geochemical data and the scale of the hyperspectral data. So we need to mix this information together. And what we get at the end is not only a map of the minerals, but it is a validated, upscaled map of also geochemical and petrological, mineralogical information. And that was one of the key aspects of our work in Vector. But we went even further than that. So if we look at this information, we can see that as, let's say, the foundation of your rock. And if you know what is in your rock, maybe we can make inferences on the geophysical information that we can gain from this rock. So if you do exploration, what you try to do is try using geophysics to find out what is the mineralogy. And here, what we have is a way maybe to combine these two information. So it means that in the future, maybe using geophysical information, we might be able to infer the mineralogy. And here, in this case, it's vice versa. Here, using mineralogical information, can we estimate what would be the petrophysical information? And we did that, and we were quite successful. You can see here, I will not bother you with the left-hand side of this slide, but you can directly focus on the right-hand side, and you see for each borehole two curves, a blue curve and an orange curve. And here what we have is the observed information, so petrophysical information, and the estimated information from the hyperspectral data. So we didn't use the petrophysical data to infer, we use the petrophysical data to train the model in order to estimate this information. So it means that using hyperspectral data, we can infer petrophysical data. So we can use that for different type of petrophysical data, and now we are going to other aspects of information that are relevant. And here's another step in this direction, because here we would be able to infer not only the petrology, the petrophysics of the data, but also get some information on rock properties that are linked to risk, for example, landslide. So is the rock stable enough, strong enough to support to be on a steep slope, for example? So that is something that we want to do in the future. And all that was developed within Vector and is open source, so it means accessible to the entire community. So that is on the 3D information or the 2D information. So, but when we want to do exploration, it's important to know that it is only one step in the evolution of a system. And what we want to know is, how did it come to that? Because then we can make prediction where we can find it elsewhere. And that was the work of Terranta, and they were developing software that include flow modeling, but also the analysis of geochemical and reactive flow. So it means not only the modeling of the flow in the rock, but also how they interact with existing rocks and where we can expect to have the deposition. And they are able to do these kind of models. And here you have two models from Ireland. And the question was, why in certain region we have deposition and why in certain region we don't have deposition, even if they are a couple of kilometers apart. And here what they found out is that just by understanding what is the overburden and erosion, so it means how much rocks were deposited on top of your potential reservoir during the evolution of the system, that at some point, if you put too much rock on the system, then you will not allow the liquid to be able to deposit it. So very, very interesting results that explain observations that we make at the surface and will also help to understand where to drill in the future in this region. And you can link that to the geophysical information that we got also in work package 3. And then you get a lot more information constraint in this digital twin. Okay, let's move on to the next aspect, integration of socioeconomic data. So as Gauthier said, we are not here to convince people. It's not what we want to do. We want to do exactly the opposite. What we want to do is to allow different shareholders, different communities to be able to have a dialogue. And you can only have a dialogue if you are informed. So what we want to do is allow the transfer of information in order to instigate a little bit more dialogue in this topic that is a little bit problematic. So for that, we develop a user interface that displays information that are relevant for the agreement on shared value. So we are not predicting shared value. What we are trying to do is trying to find the information that could be useful if you would want to discuss on this topic. So for example, social aspect, environmental aspect, and so on. So what we are trying to do here is try to find out what would be the impact of a mine on this aspect and display them on a map. And then it's for everyone to discuss. All this information is open source, provided by the EU. We are not modifying this information. We are just trying to display them in a very, very, very comprehensive way and easy way to understand. And at the end, what we get is what we call an ESG index for environmental, social, and governance index. So it doesn't tell you at all where you should or not have a mine. It tells you in a specific area which topic of interest is probably relevant to discuss and on what you should focus if you would want to reach a shared value. So for example, in some areas, it would be environmental, in some areas, probably more financial, and so on. So that's a tool that we are doing currently, and we are feeding that back to the work package 3. So Gauthier talked about that, because of course we want to improve it, and we want to make it accessible to everyone, and for sure, ensure that it is a tool for discussion and not for decision. Last topic of interest is data integration. So the idea is to have a visualization engine in order to display different kind of data. So we are talking about these digital twins. How can we display these digital twins in such a way that it is easy to use, engaging, and that enables also collaboration? I will show you that. So that is the tool. So it's based on a 3D representation of different topics. So here you have a 3D model that came from package 3. We have the position of the different boreholes that are available. But most importantly is that you can compare it and combine it with surface information. So if you want to discuss about a mine or potential mine, that gives you information about where it is, what is the size of it, what are the dimensions, where would it be, at which depths, what is the impact on, for example, aquifers, what would be the impact on the environment, what are the different zones of land use in this area, is it near to a river, is it near to a forest, is it near to a protected area, and so on. So we are not telling anyone what is the right decision, we're providing information and the way to share information in order to make a decision that would be shared by all the stakeholders. So I hope I could show you that with these tools of machine learning, we are able to add value to the data, but mostly what we are trying to do is providing the tools for a meaningful discussion and dialogue between the stakeholders. And with that, I come back to you, Sarah.
Fantastic. Thank you very, very much, Richard. So as you've seen there, we've looked at the geoscience, we've looked at the social science, and then that data science that's helping us to stitch it all together. And I think that what's really exciting with regards to all these areas is that we're making breakthroughs in all areas all of the time. So that almost tapping into the power of the ocean to understand, say, the rocks of Ireland, through to true listening to a whole range of different perspectives and thoughts and feelings with regards to raw materials. And then finally, really using the latest advances in computing power to say, well, what on earth does this look like, all puns intended? What does this look like when we bring it all together? Because it's only by being able to share that information and that data in a way that people can then visualize or can get their heads around, can you then have the next level of conversation by saying, okay, so what do we want to do, if anything? What does this actually mean for us? Be us a decision maker, or be us someone who maybe works in industry or in civil society, or whatever our backgrounds might be. Now, all of this, of course, comes with a great big dollop of ethics. And one of the other unique things about the Vector project has been the setup of our independent ethics board, etc. And to tell us about that is the person who really did establish that and made sure that it all worked. And that is the fantastic Emily. Now, Emily can't be with us here today, unfortunately, but what we do have is a video from her. So I'm going to pass over to Chris, who can hopefully play Emily's video. Over to Emily.
Brilliant. Thank you, Sarah. Hopefully that video screen is now popping up for everybody else. Unfortunately, it's not quite popping up on my screen, so I can't press play on it yet, which will be happening very shortly, I am sure, if I can find where it is hidden in the wonderful world.
Just to provide you with a bit of help there, Chris, whilst you're clicking on all of those buttons. So this is something where, when Vector was first established, of course, we had work package 1 that was led very much by the fantastic Tina, who you will see every so often popping in and out. Here we go, by the fantastic Tina that's over here. Then work package 2 is the geoscience package. Work package 3 is the social science. Work package 4 is the data science. We've hopped over work package 5. That's all about impact. That's led by Chris and myself. And then work package 6 is on the side of the ethics. Now, Chris, if you think the video is going to play, do you want to go for it again? If not,
are there, hopefully. So it should be viewable now.
Yeah, it's there.
Hello, everybody. My name is Emily, and I am the ethics coordinator for the Vector project. I've been responsible for assisting Work Package 1 to meet the ethics deliverables of Work Package 6 throughout the project, and for acting as the secretary to the Independent Ethics Committee, the IEC. Today, I'm going to take you through a whistle-stop tour of how the project has delivered on its Work Package 6 requirements throughout the project, and our key learnings on integration of the ethics requirements within the project more broadly. So the Vector project was the first Horizon EU initiative to include a mandated ethics requirements as a work package. These requirements concerned the appointment of an ethics advisor to oversee ethical issues, especially those in relation to stakeholder and public-facing work packages, and the submission of an interim and final ethics report by the ethics advisor. Initially, the Ethics Management Committee was formed in early 2023 to establish the governance and appoint the ethics advisor and monitor ethical issues. Comprised of executive board members and a secretary, the EMC was always intended as a temporary solution. And it was actually disbanded after the appointment of the ethics advisor, where governance responsibilities were transitioned. Quinton Newcomb was appointed as ethics advisor in September 2022, following a structured consultative recruitment process involving consortium input on role requirements and selection criteria. After disbanding the EMC, I was appointed as the ethics coordinator and IEC secretary, and I was responsible for ensuring communication between the IEC, ethics advisor, and project stakeholders, as well as attending executive board meetings to keep those lines of communication open. Although not required by the grant agreement, the Executive Board opted to establish an independent ethics committee, as mentioned, to support the ethics advisor with more diverse, broad expert input. So recruitment for the committee began in November 2022 and involved representatives from all work packages. The IEC was formed with Douglas Taylor, Emmanuel Gofi, and the ethics advisor, Quinton Newcomb. Since its launch in September 2023, the IEC has met 9 times and provided guidance on complex ethical issues and reviewed some of the major project deliverables like the Social Value Index and the documentary. The committee operates under a formal Memorandum of Understanding, and this MOU is aligned with the European Commission ethics guidance. So on to our learnings from integration. The Vector project, as I said, was the first of its kind to have ethics requirements imposed by the EU in the GA, and there was no guidance available at the start of the project regarding how these ethics requirements should be integrated. So as a result, it was down to the project's management committee, the executive board, to put in place appropriate governance to enable it to meet these requirements. The governance structures put in place and their component parts, so the ethics advisor, the committee, the ethics coordinator, were successful in that the IEC was able to provide independent oversight regarding various matters that arose in the course of the project. The governance structures put in place exceeded the requirements of the GA and were considered to provide a more robust framework for oversight and collaboration regarding ethical matters within which to situate the project. Integration of project ethics within the Vector project was somewhat successful. Lines of communication between the board and the committee were very strong, which enabled good collaboration between those two committees. And the IEC was able to provide advice on various ethical matters with which the executive board grappled, as well as advice on key project deliverables. The executive board and the project parties involved with these specific deliverables have found this oversight invaluable during the course of the project. I think where the project struggled to integrate its approach to ethics was really with the consortium more broadly. My role, the role of the ethics coordinator, was independent from the executive board, and I was appointed so that consortium members could bring any issues they felt necessary to the IEC directly through a neutral third party rather than involving the EB in that process. However, despite communication from the committee, from the coordinator and from the executive board about the availability of this route to the committee and various encouragements to use it, consortium members have broadly remained unengaged with project ethics, and this line of communication to the committee was definitely underutilised. Whilst we don't believe that this affected the efficacy of the committee vis-a-vis the key ethical issues that it did consider during the project, a stronger engagement from the consortium would of course have ensured a broader and more robust governance mechanism for the project, as it would have cast a much wider net for the committee in terms of the issues within its knowledge and those which it ultimately was able to consider. Nevertheless, the IEC has been key to the resolution and outcomes of many of the key project deliverables, and we hope that the success that we've had, coupled with our learnings on integration, will help others to develop robust and integrated processes and procedures for managing project ethics on future Horizon projects. Thank you very much.
Brilliant. Thank you very much, Emily, remotely. So this leaves us with only one little item to talk about. So as you've seen, we did the ethics in a slightly different and novel way, but that's one of the beauties of being able to embark on blue sky and cutting edge research. We get to experiment with new ways of doing things. And of course, that flowed through into the world of communication and into the world of impact as well. So to give us a very brief overview of some of what Work Package 5 got up to, I'm going to hand back to the fantastic Chris Stockey. Chris, back to you.
Thanks, Sarah. So we've had the joy of being involved in disseminating the project and all of the exciting outputs and results that we've heard about throughout today's call. Now, if you visit the Vector website project, which is easy to remember because it's just vectorproject.eu, you'll have seen that I've been adding it to the chat throughout this call. You'll be welcomed onto our homepage with information all about what the project is and highlights of some of the research outputs that we've made over the last 3.5 years. Now, there's lots to explore on the website. I'm not going to spoil that for you. There's further information about what the project has been doing, what the project hasn't been doing, all within the About the Project tab. The Get to Know Us tab, you can find out more about each of the project partners and what they do outside the project and the individuals collaborating inside this project through this tab here. Most importantly, perhaps, is the Vector portal. Now, for you interested in our outputs, almost all of them are stored here. Anything that is meant to be publicly accessible will appear here either through the next couple of months or already exists. So you will have seen lots of direct links being added all the way throughout this call. You can access all of the deliverables for the project, and those that are publicly available already are accessible as PDFs for download. There will be a whole load more added after the final project review in July. Publications and research papers that are open access are attached in that section. The documentary, 100 Perceptions Raw Materials, is accessible through its own webpage, as well as some of the resources that were used to run the social science study that you can learn all about within the documentary. So we'll share the trailer of that with you in a moment for those that haven't been introduced to the fantastic documentary yet. But you can access all of the materials to run that study yourself. The Who Decides game that Hertje talked about is accessible and loads through its own tab, as well as the Vector Simulator hosted on the UCD website is linked here. Videos from webinars throughout the lifetime of the project, from the very start and the launch event when we all got together and did this 2 years ago, through to specialist talks given by different independent researchers within the project. The Vector podcast, published through Spotify, as well as info packs and the geotechnical resources that Richard was talking about and Sarah Gleason were talking about as well. So the hyperspectral imaging toolkit HiWiz, and also links out to the 3D visualization platform Liquid Earth. So there's plenty to access already and more to come. If you have any questions, you can click the Contact Us page and submit a query. You can contact us through our email addresses, contact@vectorproject.eu, or find us on LinkedIn, where we'll continue to make sure you're alert of any of the updates and uploads that we make to the website. Now, I did promise that I would share the Vector documentary trailer for 100 Perceptions Raw Materials. I think it's a nice way to share some of the legacy ending. As Hertje talked about earlier, so much has changed throughout the history of this project, and this documentary represents quite a unique timestamp in that, as we filmed it earlier this year, after a lot of different geopolitical attention was being paid to critical minerals and raw materials more broadly, what they are, how we should resource them, and how we should use them moving forwards. So hopefully in a second that will be visible on your screens in a much easier way to find than before, and we can all watch and listen to the trailer.
Every single one of us relies on raw materials in order to survive. We've got 100 people who come from all aspects of society. How much do they know about the complexity and the diversity of minerals and metals that you need in something like a battery, in wind turbines and solar cells, but also in things like ventilators and also computer chips? Do people think that it is important to have the technology at any cost? Or actually, is it more important to make sure that we try not to extract any more materials out of the ground?
To understand a bit more about raw materials, how about a game? Go! You need 300 tons of steel.
We need between now and 2050 as much copper as we have mined throughout the whole of history.
We didn't have electric vehicles 20 years ago. We need to be able to generate power, and at the same time, we need to be able to save lives. Do we have enough to build all of these pieces of technology?
No. What I think is really important in this study is to make people aware of consequences of choices.
How can we make sure we do have the materials we need? We could recycle, we could mine, we could substitute. How easy is it for us to change our behaviours?
No one country on Earth has all the materials it needs. So this is very much a global problem.
We need them not only for the energy transition, but actually the future of how we want to live on this planet.
It's incredible how much we need, and I'm actually quite shocked.
What is the true cost of our dependency on raw materials, and how will it shape the future of humanity?
So if you'd like to learn more about the documentary or experience the full 29-minute version, which I wanted to show, but I didn't want to make Sarah and Hertje squirm anymore by having to watch themselves for the 100th time live with viewers. The link for that is going into the chat right now, so you can watch it either directly on YouTube or through the website page that Sarah has shared. Please do go and interact with it. It's a really interesting piece to explore the diversity of perceptions surrounding this sector that we're all so ingrained in. Thanks very much, and back to you, Sarah.
Fantastic. Thank you very, very much, Chris, for that. And thanks also for embarrassing Hertje and myself to that extent. I'm just glad that the trailer was as jumpy as it was over Zoom, which was glorious. But of course, yeah, please do go to the YouTube site, go to it through the website. You can get to it on LinkedIn. Go and check out the full documentary. As Chris mentioned, it is only 29 minutes long. And so far, the feedback that we've been getting is everybody from my 100-year-old grandmother through to my 11-year-old niece, they managed to sit through the entire thing and had something interesting to say at the end of it. So that was high praise indeed. So with regards to that, I'm going to welcome back to our stage the fantastic Richard, just for any closing comments from himself in terms of Vector as a cohesive project. As we've seen, it is composed of lots of different integrated parts all coming together. And then we're going to open for any questions. I've got a couple that have been sent in by various different means already, but if you do have questions, comments, ideas, please, now is the time to get them into the Q&A. But Richard, over to your fantastic self.
Thank you very much, Sarah. Yeah, what I wanted to say that we went through the similar process than we were explaining before of communication. So we are a very diverse consortium, so including geophysicists, machine learner, social scientists, geochemists, and so on. We are all in our bubble during most of the time. And here we had to start discussing, try to find out how we can collaborate. And I think that was a process that demanded a lot of effort from everyone. And I think we managed it. So I think this project has already been very, very positive for all the participants. So I guess, I hope. But I think it was my observation. The other observation is that it's always difficult to do things that are not usual. So to have geoscientists with social scientists in a project, trying to convince stakeholders that it is important to have this communication at all stages of exploration and even beyond is something that is difficult. The other aspect that you have seen is that we have been trying to be extremely transparent and to include ethics at all the stages of our process. We had a lot of discussion with the ethics committee, and I think it's very important also for the next project, the ISU project, to continue in this line, because what is important is transparency, respect, and also engaging in a very let's say open way with all the stakeholders, because we need to find a solution. We need the energy transition. We need to achieve this climate goal, and we can only do that if all of us are on the same boat. So I think that was very, very important for us. Thank you.
Fantastic. Thank you very, very much, Richard. Now, Richard, if I just keep you there, because we do have a number of questions, and I don't know if Sarah and Hertje want to come up to the stage as well, just so that we can all be here together. So the first question that came in is really around what are some of the legacy of Vector? So whilst the project itself, the research perhaps is done, actually it's almost like the impact is only just beginning. So what are some of those areas of legacy that we might expect to see?
So I think some of the workflows that we've developed in terms of how to deal with, for example, large data sets like all the hyperspectral data, that technology has really been rolled out in the world. A lot of geological surveys have it. A lot of companies are, employing contractors to collect those kinds of data. So I think these workflows that were developed, for example, can be applied going forwards to lots of different other studies in many different countries.
Fantastic.
So I think from a work package 3 perspective, what we added is to think beyond social license to operate. Lots of these projects focus on that concept merely. And I think what we added is a whole new space of social science where we're talking more about communication, stimulating critical thinking. How do we sort of engage people in discussions? And how do we get industry involved in these sort of discussions? So think way beyond the social license to operate concept.
Brilliant. Richard?
Yeah, and for me, I think one of the most important thing was this feedback loop that we had with this consortium. So we went from acquisition of data, going to some processing, going to machine learning, and then asking the question, but are we on the right way? And going back and trying to find out, yeah, but it's not what I need something else. Can you give it to us? And the same for social sciences. So the feedback is always going. And one of my fight that I managed to really win is that machine learning is not magic. I think I managed to convince some of my colleagues that it is not.
Well, this is a case here where that iterative approach has been really important, and almost that iteration in terms of us having the freedom to misunderstand one another as well, and then being able to actually have that level of trust and respect within the consortium that I think is still developing now, where we can say, no, I think that's rubbish. What I actually meant was this, in the politest way possible, because we do have a lot of different cultures, languages, etc., coming together. So the next question that came in is really around if we could do it all again, what would we have done differently?
What I would have suggested we could have done differently is right at the beginning of the project, we had a kickoff meeting. But I think we needed a much longer, if we could sort of go away to some cabin in the woods, the whole sort of group, and actually start off with almost like some first-year lectures that, Gershi would give the social sciences to the geosciences and the data sciences, and I could give some first-year lectures about geology and some of the terminology, and we could have had a little bit of teaching at the beginning before and getting to know everybody, on a personal level, because actually I think, as time went on, it became clear that we did need that kind of basic information and because we're all very jargon, all our sciences have their own jargons. And this makes it quite opaque to the other groups. So, yeah.
Yeah, and to add to that, I think to front load more meetings in the first year, because, it takes time to hire postdocs, researchers, and they also need to be part of the consortium nearly as soon as they come in. So if frequent meetings in the very beginning to make them part of the whole Vector family, if you like, I think I would have changed that.
Yeah, absolutely.
I think I will continue the same vein. So I think we needs to understand the power of words, and that some words can be interpreted differently, and we have to always be worried that we will not be understood, and that is frustrating sometimes, and that leads to maybe conflict. But I think we learned that during the project that sometimes we have to doubt that even our own words can be misunderstood. And if from the beginning we would have maybe had some training on that, would have maybe helped very quick.
Yeah, absolutely. I think that kind of sort of training in how to listen, but also check for understanding. So rather than assuming that somebody has understood what we're saying, actually do that circle round and check. Now, it might take longer in terms of making sure that the kind of that two-way dialogue is actually working. But I think retrospectively that might have saved us a few grey hairs over the last years. The other thing from a personal perspective, not that I think we could ever do anything about it, was Brexit, which kind of got in the middle of what we were up to. COVID was very much at the beginning of everything that was happening, but in a very kind of positive sense, I guess the attention on critical raw materials is very much here. So there's been an aspect of pull for a lot of what we've had going on there. The final question actually that has just come in through the Q&A is really around the ethics aspect. Now, I know that we don't have Emily here with us, so this is a bit tricky. But there's a question here asking us about what sort of ethics aspects might we have had to deal with. I don't think it's necessarily appropriate for us to go into any detail, of course, on this open call. But I mean, maybe actually from that social science perspective, what kind of ethics do we need to think about in research normally? Because to a physical scientist, sometimes that's an alien concept.
Yeah, but I think it's equally important for physical scientists. So in social sciences, ethics very much about you interact with people. You should do no harm. You need to have all sorts of mechanisms in place to ensure that is the case. And that's why we, in universities, we go through research ethics and explain everything we try and do. They think way more from that perspective of, interaction with people. What does that mean? But a geoscientist may also interact with communities and may not necessarily be aware of sort of the ethics considerations around it. Now, typically the work we did was low risk from an ethics point of view, but it's still important to consider, are we not, invading any privacy? Do we not, harass people? Do they have the opportunity? Are they aware they can always withdraw from conversations? So those are basic elements you would always see in research ethics.
Yeah,
one aspect as well. So just to have a governance structure within the project that is stable and robust enough to allow that we have this ethical feedback from specialists and they can judge us and provide us with information that we might not think. We are scientists. Sometimes very difficult. We are going in one direction and we tend not to look right and left. And here in this case, we have always the feeling that we can work because people are watching us. And if we do something wrong, they will tell us. So even on the governance aspect, I think it was important.
Yeah, absolutely. So I think, with regards to that, there are no more questions that have come in via the Q&A, chat, LinkedIn, or other methods. I'm going to just show that I really am in the room with these three wonderful individuals here, and just come round and say thank you very much to the camera. See, I am here. It's great, isn't it? So a massive thank you to all of the researchers, to all of the different boards that we've had involved. It's been a fantastic few years. We look forward to getting through the final reviews with regards to final sign-off to the project. If you have any further questions, comments, ideas, please do feel free to send them in via the Contact Us form on the website or via any other method. We're all about learning, we're all about improving. And I think with that, just say thank you very much, and we'll see you sometime in the near future. Thank you very much.